Hello, everybody. Please take a seat. We will start with the next session. My name is Inês Mendes, and I'm from the Research Technology Innovation team at SATSEN. And I'm sharing with Stephanie the data infrastructures and service at scale. So I will, with no further delay, introduce Andres Zielinski that will present us the Breaking the Boundaries of Earth Observation, Copernicus Data Space Ecosystem, and the Cloud Computing Paradigm. The floor is yours.
Good morning, everybody. I'm Andres Zielinski. I'm the communication person for Copernicus Data Space Ecosystem. I want to talk to you about breaking the boundaries. And then we have to think, of course, about what the boundaries are. We know that we can store a lot of data. We can also forward a lot of data over the internet. We have amazing code bases to work with data, to analyze it. I think one of the most important difficulties is how do I get started? We have smart people out there who are finding it exceedingly difficult to figure out the first steps or the first 2 weeks that you are spending with Earth observation analysis. Transferability of tools. We've talked a lot about fair science and fair data analysis, but still we find that transferability is a major difficulty. How can I check whether it's worth investing in implementing somebody else's code? Will it work on my study area? How can I give it a test? And mostly not for the people in this room, but for many, many people on this planet, one of the main limitations is simply hardware, right? How can I work with Earth observation data if I don't have hardware to store it and I don't have a powerful computer to process it? And back in 2020, when the last EO for SDGs compendium was written, which is a guide on how to use Earth observation in support of the Sustainable Development Goals, they found that the main limitation is not whether EO data exists, but whether it can be stored and accessed and in a format ready to be used. A lot of us are tackling this challenge in many different ways. I'm here to tell you what Copernicus Data Space Ecosystem is doing about it. I think that our main selling point, to put it like that, we're a free platform, but still, is that we are easy. So CDSE, Copernicus Data Space Ecosystem, is the official data gateway of the Sentinel satellites. Everybody who is distributing Sentinel data is getting it from us. We are the first one to get it as it's downlinked. Everybody else is mirroring it. This is the official platform, and it's not just a data gateway, it's a massive set of virtual machines allowing you to process the data on the cloud, and it's a code base for sharing algorithms and APIs that allow you to work with the data. So we really, really want to change the paradigm, and this paradigm shift is happening as we speak. A lot of you are already processing data on the cloud, but still, if we go out to the applied fields, to soil science, disaster management, insurance, still people are downloading data to computers and processing it locally. So in this sense, what I mean by the cloud processing paradigm is that everything happens on the remote sensor. On the remote server. Data is downlinked from the satellite to the ground. It's stored in a massive machine. This is your typical EO analysis pipeline. You are creating the pre-processing of the data, the atmospheric correction, the geometric correction, the gridding, and then we are starting to work with it, right? We apply a filter, we throw away the cloudy data sets. We apply another filter, we cut out a spatial subset of the data. We apply an algorithm. In this case, it's just highlighting the radiative power of the volcano through the shortwave infrared bands of Sentinel-2. And then, once we have done this, we have a time series of images. We want to create an end product, which in this case is an animated GIF. So these are the typical analysis steps. But in the end, most people don't want a satellite image. They want insights. They have a quantitative question that they are posing. How much is it? And then you want to create a graph. You want to visualize the data and send that to somebody's computer. And so CDSE, in this sense, is the little white arrows connecting these stages. And the cloud processing paradigm means that everything is happening in the public cloud, all the way down to the rendering of the visualization of the data analysis. And your computer is just an interface. It can be a smartphone. It can be a potato computer. It can be a 30-year-old computer. You will still be able to process the terabytes of data that are out there. So how are we making this possible? Well, at the core of Copernicus Data Space Ecosystem, it's Sentinel data. But this is a big step forward compared to the Open Science Hub that used to be before 2023, because all the data is instantly available. There's no wait for the rolling archive. If you request data from 5 years ago, it's just going to be there instantly. We have Copernicus contributing missions data, so high-resolution data served by ESA under a special license. We have terrain models and additional complementary data, Copernicus land monitoring service data to help you find the exact products that you need to use. And all this is going through APIs. So it's not just one API family we selected. We are really trying to aim for several legacy families and several open API families like Sentinel Hub and OpenEO, which are popular in the data science world and allow you to work with the data. And then the entry point for most people is Copernicus browser. So we have this free open web browser that allows you to actually get your hands dirty with the data. This is functional for school children or for non-professionals as well as professionals. You can actually start working in very, very easy steps with the data on any web browser. And we have the code repositories. Again, this is a starting point, but it also includes operational-ready end-to-end processing pipelines, which you can then pick to pieces and adapt for your code. And the big thing is the cloud computing capacity. So ESA and the Commission are essentially handing out virtual machines for free. You get a substantial virtual machine capacity, anybody who registers to CDSC, that allows you to actually perform regional scale analysis on the cloud without downloading the data. And the cloud computing capacity and the onboard repositories come together in our Jupyter lab and in our graphical interfaces to code development. And then we have a federation service. We want to, we can't be the one platform to rule them all. We want to enable people to bring together data from different backends. And we have a traceability service where you can verify the genuine originality of the data. And this counts a lot where it's used for legal procedures. I'm speaking about CAPA monitoring, for example. So all this put together is the ecosystem. So do we have the data you need? Probably yes. I mean, we have all the open Sentinel data, and this also includes some analysis-ready mosaics. So we have quarterly Sentinel-2 mosaics. We have monthly Sentinel-1 mosaics, which are really, really machine learning ready, again, because they are gridded, they are seamless, they are clean. We have high-resolution VHR data from the Copernicus contributing missions. And now, recently, we have integrated the Copernicus land monitoring service. And if you want to know more about this, then come to my demo at 6 o'clock in the evening. So a lot of downstream products which are calibrated, they're not satellite images, they are actual biophysical quantities that are also available with the same API framework and with the same coding tools. And so, is it fast? Well, of course it's fast. It's a massive cloud processing platform. In most cases, it's a lot faster than downloading the data and processing it locally. We did a benchmark. It was published by my colleague William Ray at EGU last year, where we looked at a use case, harvest detection in a couple of agricultural fields, and it's at least 2 orders of magnitude faster than pulling the data down and processing it on your local computer. Is it free? It's free, but not as in free beer. You can't there is a quota. There is a limitation to what you can do. Of course, we don't want anybody to break the system. If you need more than this quota, you can apply for a Copernicus service level user, because institutions who are providing data for the Copernicus services are eligible to process their data on CDSC, even at very large volumes. And we also have commercial processing options, so you can use the very same APIs, the very same code on CREODIAS or OTC through a commercial account if you want to use more than this quota. So how do you actually get coding? If you're not into EO coding yet, then you can start prototyping in the browser. And here the APIs are really, again, changing the game, because you don't have to worry about the data backend. You don't have to worry about where the data is coming from. You don't have to think about the visualization either. So maybe it's just 5 lines of code that you're actually editing, your spectral index, your visualization, and what you're doing with it. And when you've figured that one out, then you can take it all into Jupyter, and then you can build a notebook or take it to your local coding environment. So this enables time series, data fusion, multiple sensors, but we also have the OpenEO API, which is compatible with ONNX. So some high-end machine learning and deep learning is also enabled, and it also runs on the cloud. And we really want to build an ecosystem of service providers. So built on top of these data sets and these APIs, we already have many industry and public agents who are serving data or creating solutions. We want to bring these teams together into an ecosystem where there's an exchange of knowledge and where from these platform users can find what they are building. So how is this actually changing the game? I think most of us remember sitting around and waiting for your data to be downloaded. That's really over. That's really over. You're not downloading data anymore. Your local hardware is not a limitation, and you can connect data from different backends. You can bring together from one API data from one resource and the other one, and process them together. And again, if you're in the startup business or if you're a public agency that would have to procure a data infrastructure, this is done for you now. So you can build first, and then you can scale up as you grow. There's no need to invest in the beginning. This is a little example I have here. SatCam is actually an outdoor hiking map, which you can use on your smartphone. And the blue layer is a Copernicus-based snow layer, which is updated with every satellite image that comes in. So it really displays the current snow cover, which is super important if you're skiing or mountaineering. The vegetation layers are coming from Copernicus Land Monitoring Service, and the topography is also high-resolution open data, which can be brought together in this platform. So again, this can be directly queried through the APIs and run on the user's machine. So now, data is really accessible to everyone with an internet connection. We are really working hard to change the learning curve from very steep to incremental steps one by one. And we are serving all these machine learning-ready data sets, which are clean, seamless, gridded, and then you don't have to worry about the data preparing and the data grinding, which is usually the largest phase of a machine learning application. Data gravity means a big platform with a lot of data is going to attract more data. Now, right now, we have 450,000 registered users and 25,000 active users a week. So this is really actively used. And when we get a large community, I think we get a lot of knowledge transfer as well. So Copernicus Data Space Ecosystem is not just a data source. It's not just a cloud platform. It's an interface for knowledge exchange, for data analytics in a collaborative way. And it allows you to move from building something in the open domain to the commercial domain, and then to build services, and on top of this, of course, to foster Europe's leadership in EO. Thank you so much.
Thank you very much, Andras. I think we have time for 1 or 2 questions, if there are already questions. So then I will start. So for CDSE, can you share some insights? Who is your standard user? And maybe also what is the most used service you currently see in CDSE?
Well, the most used service is definitely Copernicus Browser. So we have hundreds of thousands of Copernicus browser users. These are people who are just quickly looking up a satellite image for whatever reason, preparation of field work or checking their agricultural parcel. There are also schools, and education of Earth observation is a heavy user. So by number, most of our users are really beginners who are getting exploring with Copernicus browser. By data volume processed, our heaviest users are probably agricultural monitoring agencies, so national cap monitoring agencies who have to look through a whole country. Many of these are now moving all of their processing to the CDSE cloud.
Okay, thank you very much. There are other questions from the audience. Okay, so in view of time, thank you very much again for Andras. And our next speaker is Dejan Shamatsiev. I'm so sorry for the German pronunciation. And he will be talking about enabling fair and open Earth system science with Earth code. The floor is yours.
Thank you. Good morning, everyone. I'm Dejan Shamatsiev from Lampada. I'm a data scientist, and we are leading the outreach and data stewardship for Earth code. Today, I'll talk a bit about open science, fair principles, and how those get turned from an aspiration to a daily practice with ESA's initiative Earth Code. We have a couple of sessions throughout this week. If you would like to engage with us, just share some questions, comments, and ideas about how to get engaged with the community, please scan this QR code. So, open science. How do we define open science? As part of its 2024 strategy, ESA defines open science as 8 key pillars, starting from open data, open code, connected between the data and the code onto reproducible platforms, all available via open access and described in rich metadata. And finally, one community drive to make this a sustainable process rather than a one-off initiative is to build educational resources, the community around it, forums, engagements, hackathons, and essentially getting the community involved into the movement. So beyond just an acronym, the FAIR principles describe what data needs to look like for it to be machine readable and machine actionable. And that's really the key aspect of it. In the core vision of making data open, it needs to be fair for it to be effectively open and usable. So those 2 terms don't really mean the same thing. There's a difference between fair and open. And What does that mean is, well, think of the example of medical data. That data can be very well described with rich metadata. It can be quality. It can have identifiers and so on and so forth, but it will be closed and it will be only accessible towards people who with restricted access. Essentially, those two principles, open and fair, whenever they're combined, that's where we get the most out of our research outputs, and that's where the greatest value is in between both. So at the moment, unfortunately, we are not, as a society, making the most of our research investments. As data, even when it's open, it's not really as fair described as it should be. We're not really putting the data outputs and the digital objects we produce as part of our research as first-class citizens. So if we do that, what does that look like? Well, whenever we have a new data set, it would be essentially uploaded somewhere on a central catalog. It would be assigned a DOI, a persistent identifier. It would be persisted in storage somewhere for the long term. It would be open access. It would be accessible via user-friendly interfaces, APIs, and so on that are interoperable for the community. It would follow conventions like the CF conventions for EO data. It would use interoperable formats, and it would be cloud-friendly to essentially enable mass processing of this data. So essentially, the gap there to getting there is defined in key 4 steps by the strategy. It's essentially the ability to access and process satellite and in-situ data in collaborative environments. It's the ability to develop and publish reusable code and data and workflows. It's the ability to validate the outputs and share the reproducible results. And finally, collaboration across institutional disciplinary boundaries and national boundaries. So what does this fair infrastructure look like that implements these? Well, we have a notion of data that's somewhere on the web. We have a notion of workflows that produce the data that's connected to it, which gives us a provenance, an idea about what code was used, what methods were used, so on and so forth. We have a containerized executable of that code, as well as a Docker container maybe, or an application package, or an OpenEO process graph. And we have the fair metadata that describes the platform used to execute this code that produced the data. And this is becoming more and more important as the infrastructure that we're using to produce, to run the tools that produce the data are moving to the cloud next to the data to support the compute next to data sort of paradigm and to enable massive, massive data sets, computations and big data. So how do we make that happen is via one of the initiatives with ESA called EarthCode, and that stands for Earth Sciences Collaborative Open Development Environment. The idea is to support this journey, to provide this infrastructure for fair and open science, and essentially provide support for Earth action to happen across ESA research. What does it do? Effectively, it bundles up and links data, workflows, the papers, the methods that were used to produce the data, makes them accessible via something called the Open Science Catalog. It enriches them with rich metadata so as to improve interoperability between other uses and research use cases. It includes the platforms as an ecosystem so as to provide the reproducibility of those experiments that were published to EarthCode. How that looks like by sort of functions is we have something called the EarthCode portal, and that is essentially the app access, the web access for any resources that you'll find on EarthCode. There you'll be able to explore key offerings, as in what platforms are integrated, things like, for example, what research is available there, access to the Open Science Catalog, and so on and so forth. The Open Science Data Catalog is where the actual data and metadata is stored, and this is the verification process of the data that gets published from research. Essentially, it's described in Stack. The front end is a Stack browser. We try and use standard metadata to make it as interoperable as possible. So that means CF conventions. It means we use standard data formats that are cloud-friendly, such as ZAR, flat geobuffs, so on and so forth, COGS. And we make it open to the community. It's all available on Git. If you scan this QR code, it will take you to the website. And this is what it looks like in effect. The front end, it's essentially a Stack browser visualizing the Stack items that are connected to the data. You can browse through the different products that get published. For example, this Ceasefire DataCube product is essentially a modeling exercise for seasonal fires. In it, you'll be able to see a rich ontology of data, metadata that describe. All of that is essentially stored as a Stack item on GitHub, which is accessible and open to the public. The metadata also connects to the actual data, which you would be able to go and load in directly via standard APIs using tools like Xarray, OpenEO, Xcube, and so on. So to enable essentially the development of this code and the publishing of this code, we have something called the integrated platforms. And essentially now we have about 8 platforms integrated into the Earth code environment, with more to come every year. The idea of these integrated platforms is that they provide a sort of common functionality between them. So that would be something like SSO, where you are able to log in with the same credentials to every platform. You would be able to have access to workflow development tooling. So you would, for example, in OpenEO, you would have something like a GUI editor, or you would have the APIs available there. And other platforms will offer different tools. We have something like, let's say, the PanGeo ecosystem offers DAS clusters and so on and so forth to enable the workflow development that supports what the community needs. We have each platform, most importantly, has different data that it has available. And this is what you would typically be interested when you are looking through these platforms, is what data, what massive archives of data do I have access to if I use this platform, which can bring all the workflows I'm running next to the cloud, next to the compute that's going to happen on that data. So there's some common functionality between those platforms, and they all offer it in different ways. One thing they all share in common, though, is a way to publish automatically to Earth code and enrich the metadata and the data you publish. So this is the idea here is essentially to turn the fair principles from an aspiration to a daily practice by automating them and putting them directly into the platforms and the workflow. So how does that work? Well, essentially, you would be able to publish data you produced onto one of these platforms at a click of a button. It would produce the metadata and publish it directly to the Stack catalog you just saw on the Open Science catalog. In there, basically, the data would be verified, and the platform workflows will be interoperable via standard metadata. So what that means is essentially if I develop something on one platform, it would be cross-functional on other platforms that implement similar backends. Let's say I work on something and produce an OpenEO workflow, then publish it to the Open Science catalog via common metadata formats. It would essentially be consumable via other platforms that have the same OpenEO backend accessible to them. These platforms are also sponsored by the ESA network of resources. So for anybody interested in running pre-commercial projects or interested in using these platforms, you can make an application and ESA would sponsor the use for you for these platforms. It's a fairly straightforward process to do so, and they're very quick to respond. So how to get involved into Earth code? We essentially have 3 user groups that we cater to. First of all, it's the ESA research projects, and that is people who get funding from ESA member states or ESA directly. What they will benefit from is they can publish directly their work automatically onto the Earth code platform. They will be able to use the platforms to develop their work, and so on and so forth. The bigger community is the community of users, scientists, and developers. And they would essentially have the ability to use the data directly that's published onto the Open Science catalog, engage with the scientific community, build the tools, publish their workflows, make them accessible to the scientists and to the wider geospatial community. And finally, we have the platform providers. The platform providers essentially are the ecosystem of the integrated platforms that provide the workflows and the fair infrastructure for scientists and developers. Essentially, if you're running a platform for Earth observation, you can get in touch with Earth code, and we would help integrate your platform into the ecosystem if you make an application. How does publishing work in Earth code? It's a very straightforward process. Essentially, the data is typically going to be packaged up automatically by one of the platforms, and then it will get reviewed by a data steward at the end of it, and we then curate manually the Open Science catalog. So every request is reviewed manually, and that's how we ensure quality of the data. If you would like to get in touch and engage with Earth code, there's many different ways. We have a couple of sessions running throughout this week as well. Please get in touch via LinkedIn and follow us for more updates. And thank you for the time.
Thank you very much, and also for keeping the time. We have some time for questions. Yeah, there's one.
Okay, thank you very much for this very important initiative. Having in mind that researchers are mainly interested, firstly, to publish manuscripts, my question would be, How well is this connected or integrated with publishers like Elsevier or something like so? Are they accepting these contributions as data repository, or are they forcing scientists to publish still on their own platforms, websites, and so on? So basically, researchers have twice the effort to make it work on probably the publishers' websites and repositories and on the ESA's offered opportunity.
So it really depends on the publisher is the answer here, but essentially what EarthCode does via, let's say, the project's result repository, which is the persistent storage, it tries to support long-term data access for the requirements of most publishers. So it covers that and then enriches the data as well so as to essentially make it ready for a data publication. And it really depends on the publishers themselves as to whether they would accept it. So it's a sort of per case basis, but there is an effort to make it aligned.
So you're talking to these publishers and trying to connect to them, or are you just simply, I'd say, waiting for them to reach out to you, or just wait whether they accept contributions to your site?
So at the moment, the project is fairly early on, and what we're trying to do is make sure we align the standards for the publishing houses to make sure that the technical requirements are covered, and then there will be future engagements with them.
Thank you.
Thank you very much. Is there any other question? Yes.
Got a question over there.
Thank you so much for the presentation and for working on this. I have a question related to the sustainability of the initiative. Will this be, there are any plans of having this open science catalog online working in 10, 15 years from now?
Yeah,
Thank
so
you.
there is long-term funding from the Future EO program for EarthCode, and it's one of the strategic initiatives at the moment. So yes, is the short answer.
Thank you very much. We will thank you for your presentation. If anybody else has other questions, he can approach you in the coffee break.
Thank you.
Thank you. Milutin Milenkovic. They will going to present us the GeoOpen Hack, an initiative on big geospatial data processing with open computing infrastructure and open tools. The floor is yours.
Thank you very much. So I'm Milutin Milenkovic, a researcher at the International Institute for Applied System Analysis. And I would like to thank for the opportunity to talk about the GeoOpen Hack. This is a hackathon we organized last year at the Institute about different ways of processing big geospatial data on HPC, high performance computing. And before starting speaking about the hackathon itself, just as a background information about the Open Earth Monitor project. So this is the project under which we initialized this hackathon, and it's quite a big European Commission project, 23 partners, and the project is, in essence, about providing a new open source tools and open data to support the fair science. We are doing that through 32 use cases, and there is also the app that presents those use cases as well. And on the bottom of the slides, you can see 3 different channels how we actually engage with users, because this is a big aspect of this project to get the feedback and co-develop the tools with the user feedback. One of those communication channels are a series of hackathons. So GeoOpen Hack was in 2024 was one part of this. And what is important to mention about GeoOpen Hack is that it's non-profit give and take initiative. So the give part is basically to support novice users to onboard on HPC computing, to lower the barrier for them, also to give them the overview of the possible open tools that can be applied on HPC, and also to identify the current gaps in big data computations. So that are the kind of the things that we try to do on those hackathons. The take part is actually the part where we would like to hear from the users, hear their feedback on the tools that we are presenting, and actually get their input how to improve this. So on the bottom again, you can see that within the project, Open Earth Monitor project, we had several products, and one part of the pipeline before publishing the project is the user feedback. So we also use the hackathon to do this. Which kind of HPC approaches we had at the hackathon? So the first 3 days we focus on direct processing on HPC. This is on the very, it's actually on the very left side of the slide, and the first day was only about the Slurm and batch processing and how to use existing open tools and apply them on a supercomputer. On this occasion, I would like to thank to the Dutch National Scientific Infrastructure that they provided us access to the Spider supercomputer, so we were doing all the processing there. The second day was dedicated only on Python, how one can do the Python code, the Python scripting, and then applying on HPC. And the third day of direct processing was dedicated on how one can apply machine learning workflows on HPC. Then we had the 1 day dedicated to Pangeo, and the Pangeo was working on another backend, European Open Science Cloud. And also we had another day dedicated for OpenEO platform that was operating on Copernicus data space ecosystem. So you can see, like, in 1 week we had every day we were working on different topics. Due to the time, I will skip this slide. This is just agenda that I more or less explained in a previous slide. This is about the participants. So we had about 41 participants, 20 on-site, 21 online. In total, 63 persons involved, like including keynote speakers and teachers. And the participants were mostly coming from Europe, though we had a good world coverage. About the profile of the participants, they are mostly coming from natural scientists or environmental scientists, ecologists, geographers. Every 5th person was with a technical background. Yeah, so that's important to know, because we also did the pre-hackathon questionnaire and after-hackathon questionnaire that would like to present, so that you can relate the results with the profile of the users we had. And of course, we had mostly academia participants. Unfortunately, only 2.6% from the private sector. That was quite striking results. We in a pre-questionnaire for the hackathon, we asked about their big data projects and how they deal, which amount of data they have, how they store the data locally, or they use maybe online data, and which kind of topics they are covering. So the results is that it's still majority of the users are having the local data, and this local data is mostly on a gigabyte scale, and about 20% they have the local data on a terabyte scale as well. And the topics they are dealing with is mostly land monitoring, agriculture, vegetation, hydrology hazards. So those are the topics they are having. It was after the hackathon, we also ran another questionnaire when we presented all those approaches, and we asked them if about their opinion on open tools on HPC, and if will they continue using them, and almost 90% of the participants said that they will continue using such kind of tools. Interestingly enough, they were all into the direct processing on HPC, even though on the bottom you can see the challenges they reported to us. So basically this direct processing on HPC was the most challenging for them, but still they prefer this way of computation compared to others, compared to OpenEO or PanGeo. So although every third also considered those two approaches. Maybe one caveat for Open Earth Monitor machine learning pipeline that we presented. It was presented actually on the last day of the hackathon, just 1.5 hour session. So many people were overwhelmed with many different approaches till then. So the timing was not so great. So I think one of the reasons why we didn't have such a good response on Open Earth Monitor machine learning approach was this, and you can see on the bottom right corner that even one of the users said I haven't covered it at all. So they were quite they were also complaining that yeah, so it was too much for 1 week to comprehend. So this could be the reason also for that result. Speaking about their perception on data volume and backends for the next project, so they are mostly dealing with big data projects for 100 gigabytes to 20 terabytes. So that's the kind of the size of the project. There is just about 10-20% of the users that are using 500 terabytes of data or more for their projects. And then we also ask which kind of backends they would prefer to use. The distribution was more evenly. We offered CDSE, European Open Science Cloud, the National Scientific Computing Infrastructure, global commercial backends, European commercial backends, and in-house infrastructure. And interestingly enough, they are all mostly interested for in-house infrastructure and CDSE. That's quite interesting. Also, another interesting aspect of this result is that looking at the European initiatives, they are more towards combined or let's say the umbrella initiatives like CDSE than going to individual backends, individual European commercial backends. That's also quite interesting. Here I just wanted to highlight their perception again on open source tools and data. So they will, of course, they are all interested in continuing using open source tools and data. For HPC, as I already showed in previous slides, it's a little bit less, but they are still quite positive about those approaches. And one of the goals of the hackathon was to enable them, because they were all novice with HPC approaches, to enable them for their next big data project select appropriate HPC approach. And every third actually said that they are, after the hackathon, confident to select that. 2/3 of them were less confident. So they still didn't say no, they are not confident. So there is we cannot say fully successful story, but at least we moved most of them that they got some idea about the landscape. In the conclusions, what I would like to show is that I would like again to highlight that having only less than 3% participants from the industry was quite disappointing for us. Of course, we targeted also a little bit academia mostly, but I think collaboration between industry and open open source community. It's very important. I think we can benefit a lot from one another. We know that there are excellent examples of this collaboration in US, in Europe, all around. So this is very important, and this, I think, in the future will be a focus of the hackathon, that we focus more on attracting the industry people coming and working together with us. About the typical big data projects, so people are still dealing with local data, so they are still on a gigabyte level. More than 70% of the big data projects will be dealing with data volumes of 100 giga to 10 terabytes. And most of those users would prefer the local infrastructure or CDSE, and they prefer the direct processing on HPC the most. So those are kind of, so this is a kind of a profile of the environmental scientists dealing with big data. At the end, I would like also to conclude that, that all the participants actually answered that they would recommend the hackathon to others to attend. And I would also like, it's last but of course not least, we had a one-time budget for this hackathon last year, and of course we are looking to continue this maybe every second year, and I would be very happy to discuss with you if we have any ideas how we can continue with this initiative in the future. So thank you very much.
Thank you very much. We have time for one quick question from the audience. No, then I have a question. You did mention you would be interested in continuing the hackathon, so I think the data you showed from what participants report, what is useful for them, what they actually use, is in itself super interesting for many people that are designing these type of, let's say, services, software, workflows. Is there an idea of maybe making this a bigger, let's say, research topic, and thinking about basically bringing light into who these, the majority of HPC users are?
Yes, so that would be also one idea. It's also part of this Open Earth Monitor project, that we engage with the users and really profile their sense what they wish from the supercomputing, what is the typical project they are dealing with, where they would like to do, and also to engage with different backends and approaches, and include them in a hackathon and present them. So that's
okay. Will that
we would like to continue.
Will that be published, and when?
Yeah, those kind of research is not so easy to publish. So we are happy to publish it as a conference paper or as a blog, or so it will be for sure shared and published openly. So we are fully open, and we would like to bring this back to the community. I'm not sure if this is a really scientific paper, yeah, but maybe on this type of conferences we can report on that. Yeah.
Okay, and BiDS'25 then. Thank you very much.
Yeah, thank you.
Round of applause. And our next speaker in this session is Andrea Colapiccioni, who will be talking about Retrieve, Transform, Deliver, integrating preservation and performance in the EUMETSAT data lake. Thank you very much.
Thank you. I'm Andrea Colapiccioni. I work for EUMETSAT as Enterprise Data Architect. And in the title, you have the what we are going to do. So with the first slide, then I cover what we are going to do. That is to try to have a synergy between our data preservation and our EUMETSAT data lake, that is the place in which we store all our data. So let's try to start from the tools that we have to distribute the data to our user. We use two mainly different channels. One is a push channel. So this means that we are streaming in broadcast, in multicast, the data directly to the user. We use mainly two channels. One is the satellite UMETcast that use the satellite and a satellite dish to the user receiving station, and the terrestrial UMETcast that it uses GEANT mainly to distribute data. And then we have the pool services. With the pool service, we have the data store. It is our unique interface to go and to get all the data. That is supported by the data tailor. There is an infrastructure to change the format of the data that you want to download. And we have UMETView that is for visualization and to have interactive visualization of the data. Then we have the long-term archive that is used to preserve all our data. Some facts and figures. So we have more than 55 million of products available on our data lake. Every month, we ingest more or less 3.5 million of products. This means that we have now 7.5 petabytes of data stored. Not all are available, because not all are user product, so there are also internal product with an availability of more than 99%. In average, our 1,000 unique users are downloading 1 petabyte in average from the data store, and we have 20 million in average of successfully delivered. Our data are divided in collections, and we have more than 800 different collections. Out of them, 146 are visible in the catalog. We have 7 petabytes, but the trend is that in 10 years, we will have 100 petabytes to be stored and distributed. Because we have the new missions, like the EUMETSAT Polar Seasat second generation, we have the Meteosat satellite, the Copernicus missions, SAF data, third-party data, and also we have a lot of different formats to handle, because we have from legacy format, like we have GRIP, we have NetCDF, we have cloud optimized, no, but we have ZAR, that is the future. So sometimes we have also to duplicate the data. But I would like to show what does it mean to store and handle 100 petabytes of data, because 100 petabytes is a difficult number to be understood. So let's try to analyze from a cost perspective. Let's say that I'm a private individual, and I want to store 100 petabytes on a public cloud, maybe on a very well-known cloud with the name of the river. This means that it costs 0.2 cents per gig. So to store 100 petabytes, it means that you have to pay 23 million euro per year. Access time is instant. It's wonderful for real-time analytics, operation data, frequent access. Or you can buy an appliance and you can store at your premises, is what we do. But to store everything in the same appliance is not a very bright idea, because everything tends to break. And so it means that 100 petabytes can easily become 200 petabytes to handle. And then you have to put the operational cost, the power, the spacing. So a monolithic approach is not sustainable and is not efficient. Let's imagine that you want to use an archive, a cool tier, that is also offered, using the same cloud provider. So the cost for 100 petabytes became 4 million per year. Access time is hour, so you ask for the data, and then after 12 hours, it's available. And it's very good for long-term data retention, compliance, and frequent access. And now, let's try to think, what does it mean to store on tape, for example, so for a deep archive. An LTO tape, uncompressed, can keep up to 18 terabytes on a tape. On a 2.5 to 1 compression, you can store 45 terabytes. So it means to store 100 petabytes, you need from 2,000 tapes to more than 5,500 tapes. The cost of one tape is 100 euros, more or less, street price. So it means that it costs you from 200,000 euros to 500,000 euros. So the access is days to week, and it's best for digital preservation. Of course, you have to keep your data redundant also on tapes, because if you are vintage, like me, you remember that when we had these beautiful music tapes that you listen again and again, sometimes your tapes becomes unreadable and you lose all your music. So there's another physical constraint, that is the gravity, because the data tends to be attached to the place in which you store. So there's moving 100 petabyte, it's a project per se, because via a 10 gigabit network, it takes 2.8 years to move 100 petabytes. So not considering latency, retries, and everything. So if you have a dedicated network, it takes almost 3 years. Full restore from tape library, so if you have 8 drives that can read up 400 megabytes per second, it takes 1 year to restore everything. So, recommendation. The access to our data is not uniform. So we have collections that are mostly accessed in the first days after the publication. So for example, our Mediasat data, in the first 3 days, everybody wants to download the data, and maybe after 1 year, the interest goes down. For other type of data, for example, for the level 0 and the auxiliary file, we need only every 2 years that we have a reprocessing campaign, so there's no need to keep it online and available. So you can think ahead and then store on tape and then move back. So this means that you have to adopt lifecycle policies, and we need tiered access to the data to ensure that cost control and operational readiness. So depending on a single appliance poses a risk of total data loss. That's why we are running an initiative that is called Long-Term Data Preservation Access Management Evolution Initiative. We like very long titles. It's called Friendly LTDPA. So with this initiative, we are modernizing our long-term archive service, and currently it was open since a few months ago also for the user to download data, and now we are closing, and we will provide a unique access to the data to a unique interface. So the long-term archive will become more or less readable only from inside. We are building a sustainable data governance model, so with performant and reliable access to data in a cost-effective manner, and a sustainable data governance model. We try to apply a very simple paradigm, that is retrieve, transform, and deliver. So it means retrieve the data from the optimal tier, so online, on archival. So the source can be our UMETSA data lake, or LTA, that is the long-term archive, that is our deep storage. We will be able to transform the data on the fly, so doing subsetting, reformatting, reprojection, and the component is the reuse of the data tailor that I showed before, and a new component that is called order and job management, that is an orchestrator of this, and deliver the output to delivery point. That can be an S3 bucket, for example, or the European Weather Cloud. We have also destinationers, and the control is under role-based access control, quotas approval, and other beautiful, let's say, paradigm. Or the right data in the right format, in the right place, on demand. So now let's see how we do it. We are going to build a user-facing interface, so both UI and APIs, and we will also provide library to help the user that will command the direct download, synchronous download, the ordering, that will be asynchronous, and it will make the access to the delivery point. Behind the scene, we have the orbital job management for the orchestration, so in which we want to have predictable scheduling quotas, fast-track option for efficient order and job management. And this order and job management will ask to the LTA, the long-term data preservation, the data, and also will use the UMETSA data lake with this multi-tier storage. It will also come on this data tailor for the data transformation. Just two very quick example scenarios. So our reprocessing team wants to do a reprocessing campaign. So it means they order the entire mission level 0 and auxiliary file. Data is retrieved from LTA, delivered to a private target location. They do the process, and the data is archived and reorganized back in the EDL data store where it's made accessible to the user. The other scenario can be, for example, a requested data subset for one collection in ZAR for an internal proof of concept, for example. So we retrieve and transform. On the fly, we transform on, for example, a single file based, and we deliver, and then the user can access the data. So timeline. We are at increment 0. We just end the increment 0, in which we are going to finalize the user and system requirement. We do a preliminary architectural design, and we do proof of concept. Then we have 3 increments. So the end of the project is for the end of 2027, in which we do the, let's say, the actual development. That's why I don't have fancy videos to show what we are doing, because we are going to build this. And this ends my presentation. And thank you, questioner, welcomed, and I think I'm time.
Thank you very much. We have time for one question, if the public has any question. Okay, if not, we move on. Thank you very much.
Thank you.
Now we have Pablo Garcia that is going to present us the GSSC, is a thematic exploitation platform for navigation digital transformation, enhancing GNSS scientific research. The floor is yours.
Thank you. Hi, friends, dear colleagues. I'm going to tell you about the GSSC project. So, over the past decade, the volume, diversity, and scientific relevance of the globally navigation satellite system data have grown significantly. This expansion has been driven not only by the increasing number of satellites and ground stations, but also by the integration of GNSS sensors into spaceboard platforms and mass market devices. However, this growth has also introduced many technical and organizational challenges. The data has been historically spread across a fragmented landscape of archives, often using non-standardized formats, and very limited in discoverability, and with a lack of tools for efficient analysis. So in response to this limitation, the European Space Agency established the GNSS Science Support Center, or GSSC, located at European Space Astronomy Center, the SAC in Madrid, Spain, from where I came from. The GSSC aims to enhance and streamline the scientific use of the GNSS data by providing a platform that supports data centralization, access, processing, visualization, and analysis under a very unified framework. So, designed as a thematic exploitation platform, its mission extends beyond simple data access, focusing instead on creating an open, integrated environment that supports the entire research lifecycle. At the heart of this ecosystem is GSSC Now portal, the interface of the platform which integrates powerful search engines, RESTful APIs, graphical explorers, and in-browser scientific tools. Enable direct interaction with massive files without local downloads, while embracing the FAIR principles, ensuring that way that the data is not only available, but also is well documented in a way that facilitates discovery and their reuse across the very scientific domains. Okay. And at the core of this GSSC lies it federates data archive and integrated data lake infrastructure. That is an essential component that enables reliable, high-throughput access to diverse GNSS datasets and is designed for long-term preservation, rapid indexing, and on-demand availability. This archive ingests and harmonizes data from both spaceborne and terrestrial sources, providing access to almost 300 millions of data resources, millions of individual data sets. And these resources include many observation data, like RINEX formatted observations from ground-based receivers, also navigation data, like K-satellite broadcast products such as ephemerides, orbit and clock solutions, DCD files, or ionospheric corrections. We have also atmospheric products, that is derived data set that provide critical insights into atmospheric variability, and of course space element data, like onboard telemetry from receivers aboard the ESA's satellites such as Galileo, Sentinel, Swarm, and the like. All of them, of course, formatted under the community standards, like RINEX 234, SP3, IONEX, and the like. A significant innovation of the portal is its interactive map-based search interface. Unlike the conventional FTP directories or static directory structures, the JCC Explorer allows users to query a dataset based on multiple attributes, which include geographic bounding boxes, station locations, or maybe time ranges, or like storm periods, mission phases. Also, you can search by GNSS constellations like GPS or Galileo or BeiDo or GLONASS. Many observation parameters, signal type, frequencies, and more. So this interface not only accelerates the data discovery, but also enhances the user experience, especially for multidisciplinary researchers, which can be unfamiliar with the GNSS data hierarchies that can be a lot which will have a lot of complexity. Talking about the architecture and taking a look into the insights, is designed as a modular cloud-native platform built on containerized microservices and orchestrated through Kubernetes. This design enables independent deployment, maintenance, the easy scaling of the core services, which are structured around three primary functional layers. The first one, the ingestion services, is responsible for ingestion, storage, and classification of the data. All of these resources are validated and enriched with metadata, which is indexed for its efficient discovery using Elasticsearch. We have also the exploitation services, which coordinates and processes the workflow execution. And finally, the dissemination service layer, which include both graphical and programmatic interfaces. The Portal Explorer offers face-set search and map-based navigation for dataset discovery, while the RESTful APIs and the command line tools provide automation options for the more advanced users. The data labs. This is one of the most innovative features of the JCC now. The integration of browser-based computing through its data lab system. And this capability basically eliminates the needs for local software installations or high-performance computing resources. Instead, the users can launch analytical environments directly from the web browser with just a few clicks. Data labs are based on containerized execution environments managed within the ESA secure cloud infrastructure. These containers are deployed on demand and pre-configured with widely used scientific tools. Among the default options available, we have the Jupyter Labs. That is a powerful notebook-based environment for interactive computing in Python, or Octave, which is a computation tool with compatibility for MATLAB scripts. Or we have also the GLab, a tool capable of full GNSS processing, from raw RINEX files to precise positioning results. So once a data lab is launched, we have access to persistent user storage to retain intermediate sessions and notebooks across the sessions. And we have also optionally configure the GPU resources for acceleration of machine learning workloads or large-scale simulations. In summary, the data labs represent more than just tools. They are scientific workspaces designed to research, lower the technological barrier to entry, and empower the user to explore the complex GNSS datasets. And now let me tell you about a pair of use cases, just to show you how, through data labs, the GSCC now supports advanced analytics designed for machine learning, citizen science, Internet of Things-based applications, and also large-scale participatory science. For example, the Camelot Initiative picked up a collection of 50 million of observations from smartphones during a 6-month campaign. And all this data were processed within the platform for machine learning-based forecasting of tropospheric and ionospheric conditions, and are now accessible through its dedicated data labs. In parallel to that, another project like UBSAP illustrates the integration of low-cost Internet of Things sensors with GSSC workflows. So the researchers can monitor structural displacements and landslides near critical infrastructures, with all the analysis and the visualizations performed entirely within the platform, which is the beauty of the project. These examples highlight how this project not only enables scientific research, but also extends the GNSS data exploitation to public engagement and operational monitoring context. And now, looking a bit forward, we will continue to evolve the platform through several key developments. Of course, in terms of performance, security, and stability, but also working on with other space geodetic techniques data platforms, like it could be VULBI. We are expanding the APIs for integration with institutional workflows. For example, in the context of the Genesis mission of the ESA, and adding education content to support universities and training programs. So, friends, that's all from my part. I invite you to check out the platform and play a bit and have fun. And I encourage you as well to register using the form and the invitation code, the BiDS'25, just to know that you came from here and that I managed not to bore you to death with my speech. So thank you to all.
Thank you very much. We can take one question. No? So then thank you very much again to Pablo. You're around during lunch break to answer potential questions as well. And we'll move on to the last speaker of the session, Eduardo Ramani, who will talk about towards the definition of a benchmark for WMTS. The floor is yours.
Thanks. Hi, everyone. I'm Eduardo from the Joint Research Center of the European Commission. And with my colleague Michele and Peter, we would like to present to you this work. So this is my agenda for today. I would like to briefly introduce you to the context and the motivation behind this work. I would like also to present which is the research gap that we try to fill and propose our solution with some example. And then I will try to tackle briefly the conclusion with some future works. So WMTS, or the newer version with the OCG API, are everywhere. Smartphone, PC, and even AI agents start to use these kind of services because it's one of the best solutions, in my opinion, to display a big geospatial data set when you just need a piece of it. And as we said today, and also before, we are about to reach 100 petabytes of data. At GRC, we asked today 25 petabytes of data. And with the increasing amount of geospatial data that have been collected, generated, and with the increasing number of use cases, possibility, application that we can have, this kind of technologies like the WMTS becomes a key element in the digital infrastructure. However, out there are many different solutions, many technological solutions, tens of them. And with the new standards that recently came out, also new software are available. Therefore, a practitioner needs to understand which is the best solution for its situation. And assessing the performance of this kind of technology is a key element. However, to the best of my knowledge, there is no standards solution to benchmark this kind of technology. And this is where we try to start the discussion with this work, because I believe that assessing and finding a way to benchmark this kind of solution can be beneficial to many of us. But defining a benchmark of a technology is a challenge per se, because you have to think about what you want to really include in this benchmark. Otherwise, the exercise can be misleading, can lead to misleading results, right? And this is where our framework come in, because we try to start this discussion about which is the recipe, which are the main elements, ingredients that you want to have when you are trying to address what to put in a benchmark for this kind of technology. So our core, our prerequisite was to have something that is replicable, transparent, and for this kind of stuff, containerization can be a solution. It allows you to have everybody have the same environment. You can also constrain the hardware resources somehow. And also your infrastructure, in this case, the WMTS, it can be just one of many components of your digital infrastructure. So our prerequisites, something that you have to do beforehand before starting doing this exercise, is to assess the single components of your digital infrastructure to make sure that you don't have bottlenecks elsewhere. And then, when you have like the environmental set it up, you have to define what you want to perform. So the benchmark assess something, and for us, the response time. So how much time does it take to generate a request for a single tile and render it and returns back to the client. And then you have to start to hypothesize some critical elements, factors, characteristics that may lead to different results, inconsistent results when you use different technological solution, different software. In such a way, if something pops up, so if there is a difference between multiple technology, multiple software solution, means this is a hint that probably what you are measuring, these characteristics, is something that you want to account in your future and definitely benchmark. So this is a very simple setup that we put in place. So we have the WMTS that is behind the reverse proxy, and then we have the client. And the response time is just the sum of all traveling times and all the processing times of each of these elements. But in experimental condition, you can make sure that this response time is actually dominated by the processing time of the WMTS. And for testing purposes, we use Sentinel-2 data. Instead, going into some details regarding the actual technological details. For the client, we use Locust. That is a really nice library. It's written in Python, I believe, that allows you to simulate a virtual user, and each user can request multiple API requests. In our case, we request 10 tiles at a time, And you can also put in place the locus in a distributed environment in such that the workload of the client is not just on one single machine. For the reverse proxy, we use Nginx, and instead for the WMTS, we use GeoServer, a long-standing project, open source, written in Java, if I'm not wrong, and TileGeo, that is an in-house developed by GRC that combines open source technology. It's open source as well, and it's combined GDAL, Mapnik, and FastAPI. So this is our hypothesis. So we try to assess if this characteristic needs to be included, may be included in the future benchmark for this technology. The first one is the input file size. Does it matter to have a small or a terabyte geospatial dataset to handle? Does it matter if the format is a JPEG or a GeoTIFF? Does it matter if the user requests to render PNG tiles or WebP or JPEG tiles? And also, there is a difference if I'm requesting a tile very zoom in or very zoom out. So this is our just example of hypothesis that you may ask yourself and you want to investigate in your experiment. So these are the results that we get. This is not just this is not a speech to say which one is the best, but we would like to start a discussion on how we can define a benchmark for this kind of technology. Even if these two plots are next to each other, the scale are not the same. But anyhow, this is not the center of the topic. Here we are looking for inconsistency, inconsistency. So we want to see if there are inconsistency within the same software or inconsistency between two different software. For instance, for TileGeo, we see that the percentile, the 15th percentile of rendering, the average rendering time for WebP tiles, it's higher. It's significantly higher than the other formats. Instead, for GeoServer, when you ask tiles, and here we are talking about same hardware condition, same input data, but we are just measuring what the client through Locust is measuring. That if the zoom level is 7 rather than 17, you can feel a very substantial difference in response time. Same reasoning for the input file size. So this led us to discuss that, as you can see here, there are something that is different there is a different behavior given different technological solution. And this result, added to the fact that there are out there tens possible software solutions, means that we need something to help practitioners to decide what they want to use. Because I believe there is no solution that fits all needs, but we have to assess based on the business requirements of each use case, which is the best solution. And with this framework, we try to tackle this problem, and we try to give you an initial idea on how we can assess which elements needs to be included in this kind of reasoning. Of course, in the future, we plan to explore new hypotheses and verify if they are important to be included in the future benchmark, and we would like also to horizontally add new software solution to verify if such elements are important to be included. And this is all for my side. Thank you for your attention, and thank you for having me, and I'm glad to have I'm trying to reply to some question that you might have. Otherwise, I don't know if it's lunchtime.